How long would it take for a bouncing ball to finally come to rest? This is a very simple physics problem, and yet I have seen many students struggle with this problem because it involves repeated number of bounces. In fact, infinite bounces if I look at it theoretically, and therefore students have a lot of difficulty in a very simple question like this. And I've also seen questions like these come in various examinations like physics, IITJAM, TIR for physics, etc. So I want to solve this problem today to demonstrate the steps of approaching a question that involves repeated bounces or repeated collisions. So once you understand this question, you should be able to do other similar questions that involve repeated collisions or repeated bounces. So I have a question similar to this from Physics IITJAM 2024 of this year. A ball is dropped from a height h to the ground. If the coefficient of restitution is E, what is the time required for the ball to stop bouncing proportional to? All right, so I want to find out the time that it takes for a ball that experiences repeated bounces to come to rest. And the only thing that I actually need to solve a problem like this are equations of kinematics and a general understanding of the coefficient of restitution. So let me define those things first, and then I will show you the steps involved. So what is coefficient of restitution? You see, whenever collision takes place, restitution, whenever collision takes place, we want to measure the ratio of the sort of loss of energy or loss of velocity. Then we use the concept of coefficient of restitution. It simply is the ratio of the velocity or the relative velocity after a collision to the relative velocity before a collision. And because bounces are essentially collisions with the ground, therefore I can simply say that the coefficient of restitution is the velocity or the speed of the ball after a bounce has taken place to the speed of the ball before the bounce takes place. So if the ball is approaching the ground, what is its speed right before it experiences the bounce? And what is the speed right after it experiences a bounce? So if there is no loss of energy, of course, E is going to be equal to 1. But in usually realistic scenarios, there is a certain loss of energy. The velocity after the bounce or the speed after the bounce is slightly less than the speed before the bounce. So therefore, E is usually less than 1. Now, using this concept and the equations of kinematics, which are quite simple actually, for a ball that is falling through gravity. So imagine that some sort of a ball, you drop a ball and it falls through gravity. It starts with 0 speed and it reaches the ground with speed v, and let's suppose it traverses a distance of height h. In that kind of a scenario, I can apply the equations of kinematics, which is v square is equal to u square plus 2gh, where u is equal to 0, and this simply gives us the final speed v is equal to 2gh root over. So that means if a ball is falling through a height h, it gains a speed of v. Keep this in mind because I'm going to be using this expression in my steps later on. If a ball falls through a height h, it gains a speed of v. But we can say the same thing about a ball that is going upward. So for example, if a ball is thrown up with a speed of v, then it will climb the height of h. All right, because the whole motion is symmetric with respect to each other. So if a ball falls down a height h, it gains a speed of v, and if I throw the ball with a speed of v, then it will climb up a height h in this case. All right, so this is a very simple expression that I'm going to be using actually in my table. That's why I have derived it at the very beginning itself. And what is the time that it takes for this kind of a motion to take place? For that, I'm going to be using another expression, which is the distance traveled, which is the height, is equal to ut plus half gt square for a ball that is falling from a particular height, but because it falls with zero speed, therefore h is equal to half gt square, and therefore t is equal to 2h upon g root over. So this is the total amount of time it takes for a ball to fall through a height h, as well as for a ball to climb up a height of h if I throw it with a velocity v. All right, that's it. So I'm going to be using these two expressions to curate a very simple table. All right, so in the right hand side here, we have this kind of a setup that involves repeated bounces, and I have sort of separated individual bounces so that I can analyze the quantities for each of them separately. So this is bounce number 1, this is bounce number 2, this is bounce number 3, this is the 4th bounce, this is the 5th bounce, and on. However number of bounces or collisions that take place, I'm going to be looking at them one by one. And when I look at them one by one, I simply want to create a table for its speed right before and after the bounce, the height it goes up to, and the total time that it takes for that motion to take place. So for example, if we look at the first one, if we just look at the first one, then in the first case, the ball simply drops from a particular height as is given in the question. All right, the ball drops from a particular height, and that height is capital H. So this is H, and the moment it reaches the ground, or it is about to bounce, it has a certain amount of speed. I'm going to call that speed as root over 2gh, as I have demonstrated here, that if it drops a height h, it gains a speed of root 2gh, right? And of course, it drops from a height of h, and in that process, it's going to take a time of 2h upon g root over. Quite simple, right? It drops from a height h, gains a speed of this much, takes up this much amount of time. Now, the moment it experiences a bounce, what happens? If it has velocity v here, suddenly the bounce will change its velocity to ev, based on this concept of coefficient of restitution. So the velocity after the bounce is equal to e times the velocity before the bounce. So what is the velocity or the speed before the bounce? The speed before the bounce is root 2gh, right? But the speed after the bounce is e times root 2gh. That's it. So the speed after the bounce decreases by e times. So therefore, now if for the second bounce, if I write it in this fashion, for the second bounce, if the initial speed is this much, because this is the initial speed, right? So this can be written as how can I write it like this? How can I write it? So this can be written as 2g e square h. Okay. Now, let us use these expressions in its general form. Okay. So if you look at a ball that is thrown up at a speed of root over 2g e square h, then can you tell me it will climb up to what height? If you look at these expressions, it is kind of obvious that it will climb up a height of e square h, and it will take a time of 2 upon g e square h. All right. So think of this as this new height. This is this new height h dash. All right, for the second bounce. So if it is thrown up with a speed of root over 2g e square h, it will climb up a height of e square h, and it will take a time of root over 2g e square h. So this is going to be equal to e square h. So this height is e square h. But once the ball climbs up, it again comes back down. So the time that it takes in this after the second bounce is twice this time. First bounce, it just drops. Second bounce, it goes up and then comes back down again. And I can repeat this process over and over again for all the bounces. So if I look at the third bounce, then now I think it should be obvious to you that this should be equal to, again, E times 2g e square h, which can be written as 2g e cube. This should be, sorry, e to the power 4 h root over, this is the speed, right, at the after the third bounce, and therefore it should climb up to a height of e to the power 4h, and it should take a time of 2 upon g e to the power 4h root over to go up and to come back down again twice that time period. So therefore this height is simply e to the power 4h. Let me bring this table a little bit to the downward direction, okay, here, okay. Now if I look at the fourth bounce, I think now everything makes sense to you. I can repeat this process over and over again. The speed becomes e times root over 2g e to the power 4h, which is equal to 2g e to the power 6h root over. So it climbs up a height of e to the power 6h, and it takes up a time of 2 upon g e to the power 6h to go up, root over, and twice to come back down. So e to the power 6h, okay. And I can repeat this process for the next bounce. For the fifth bounce, it is going to take e to the power 8h, and on and on. So as you can see, in a theoretical problem like this, there are going to be, theoretically speaking, infinite bounces, one after another, with decreasing speeds and decreasing heights. So now what I actually want in this particular problem is that I simply want to add up all the time that it takes. That's it. Nothing else. I don't need to do anything else, because the question simply asks how long would it take for the ball to come to rest, and which is interesting because even though theoretically there are infinite bounces that are taking place, practically speaking, it leads to an infinite series that converges on a finite value. And because of this reason, the total number of, or the total time it takes for all these time periods to get added up, let's say I call this as capital T, that is a finite number which we can calculate from this summation. Okay, so let's do that. We have already done the sort of the difficult part of this problem, which is basically building this kind of a table, looking at all the physical quantities for each bounce and adding up a particular quantity, which is a time in this problem. So if I add up all the time periods, the total time taken, capital T, is simply equal to the first, for number 1, I have 2h upon g root over. For the second bounce, after the first bounce, twice of 2 upon g e square h. After the second bounce, you have 2 upon g e to the power 4h, and on and on. Let's look at all the terms involved. Twice of 2 upon g e to the power 6h, and on and on. Okay, so now what this leads to is it leads to an infinite series sum. So let me take upon and times twice common. So this becomes half plus, here we will have 2h upon g. I'll have e plus e square plus e cube plus e to the power 4 plus on and on. An infinite series. And then again, if I simplify this, this will become half plus 1, or I should say e, right? Here I'll just keep e here as a common, and this becomes 1 plus e square plus e cube plus on and on. So I end up getting this infinite GP. This is essentially a geometric series. So most of you would probably be familiar with these infinite series sum. of a geometric series. The geometric series is essentially a series of the form of this. It looks like A plus AR plus AR square plus AR cube and on. And the sum of this series is equal to A times 1 minus R to the power N upon 1 minus R. So this is a very general geometric series where A is some kind of a constant and R is a term whose power increases from 0, 1, 2, 3 in this particular manner, and the summation is A 1 minus R to the power N upon 1 minus R. But in this case, A is equal to 1. Okay, in our case, A is equal to 1. And R is equal to, essentially R is equal to E. But E is also less than 1. So we have a very specific scenario for a geometric series where R is less than 1. In that situation, the summation is specifically equal to A upon 1 minus R. Okay. So therefore, for our case, if I add up this particular series, okay, if I add up this particular series, I end up getting 2H upon G half plus E, and this should give us 1 upon 1 minus E. Let us just finish this problem. We have already done. This should give us a simpler version of the expression for our final answer. This comes out to be twice 1 minus E, and here I should get 1 minus E plus twice E. Okay, which should lead to twice 1 minus E, and this is 1 plus E. That's it. So the 2 and the 2 gets cancelled, and the total time that it finally takes, that we have obtained for a bouncing ball to come to rest, is 2H upon G, which is, by the way, the time period it takes for an object to come down a particular height, if you remember, times 1 plus E upon 1 minus E. So the question that we started with, it simply asked us this proportionality of a particular expression. So if you look at the options back again, it said the time required for the ball to stop bouncing is proportional to what? It is proportional to this, 1 plus E upon 1 minus E. All right. So we have obtained this. The option number B is the correct answer. The answer is option number B. So this is a very sort of a general expression that I've obtained for a ball that is dropped from a particular height H, and then it experiences repeated bounces for a long time. Then what is the time period it takes for the ball to finally come to rest? And this is the time that it takes for the ball to finally come to rest, and it depends upon E, which is a coefficient of restitution that gives us an idea about the relative velocity after the bounce as opposed to the velocity before the bounce with respect to the ground. Now, it may happen that you are facing a problem which is slightly different from this. And once you understand the steps involved and the method that I've employed, I think no matter what kind of a question you deal with, you should be able to solve it. You just look at all the bounces, the repeated bounces one by one in a simple table, write down all the physical quantities involved, and you should be able to obtain the answer to your problem, no matter what problem you're dealing with. For example, if I give you a very sort of a projectile kind of a object. So for example, a ball falls in an inclined manner and it experiences bounces in this particular manner. So I took a very simple case of a ball that is repeatedly experiencing bounces in a vertical direction. But what if you're dealing with a ball that is experiencing bounces in this particular manner? In this kind of a scenario, the problem actually is not really that difficult. It's actually very easy because you're only interested in the vertical speed. So the only thing that you need to do is you need to be concerned with this vertical speed. So if the vertical speed here is, let's suppose this is theta and this is, let's suppose, V, then you are interested in V sine theta. That's it. So you are only interested in V sine theta because it is a vertical speed that is going to decide what answer you are going to get at the end. and the horizontal speed isn't going to make much of a difference here. So based on V sine theta, you can do a calculation involving repeated bounces with projectile motion in the ball's trajectory. All right, that is all for today. I hope that you have learned how to do this problem in a detailed manner, and it's going to help you in your problems that you are working on. A little bit of a plug here. So for example, we have for students who are from India and preparing for different kind of examinations like physics IITJAM, TIFR, etc. We have regular live and recorded batches that are available on our Elevate Classes platform. And many students have been using our platform, and they have been selected to various institutes in this particular year. If you are interested, we have a NET batch which is starting in December for the upcoming year. You can download our Elevate Classes app and you can browse the courses. And if you're interested, you can join our course and start your preparation. That is all for today. I'm Divya Jyotidas. Thank you so much, guys. Have a nice time. I'll see you in the next video.